I had to use this picture because when I looked for something having to do with trigonometry and the X-Wing fighter came up, how could I refuse? We're talking still about solving equations. An identity is true for all values of theta or x. We're not really talking about identities. We're not solving identities today. We're doing equations. Equations are only true for specific values of theta or x. When you have an equation at the end, you will have an answer like theta equals pi over 4. When you have an identity, you're proving with a left side, right side, and you're not using any values at all, like pi over 4. You're proving that it's always true all the time. First, we're going to review some types of factoring. The first one we learned probably in grade 9 was greatest common factor. Then trinomial factoring. Some of you will use decomposition. Some of you will use a sum and product or crisscross method. They're trinomial factoring. Difference of squares. That's when you have a squared minus b squared, and you can factor that. And you could factor by grouping. That's if you have 4 terms or more. That's usually the strategy you're looking for there. And what if you can't factor and you have a quadratic? Well, then you're using the quadratic formula. Today's topic is called solving quadratic trig equations. So all that means is we're going to be solving trig equations and they're going to have some exponents in them. Example 1, solve for theta in this domain, always a restricted domain. And look at degrees, yay! So for those of you who just hate working with radians, this one's in degrees. We need to solve for theta. The problem is here we have 2 different angles. We have the 2 theta and a theta here. We need matching arguments, is another way of phrasing it, of trig functions. So we have a double angle here and a single angle here. That's a bit of a problem. We also have a cos and a sine. So to solve any equation, and I talked about this a bit on our last video, if you had 2x plus 3y equals 5, you can't solve that because we've got too many variables. So we need to take this y, for example, and change it to an x, then we can solve that. So we're going to work on this right here. So we notice that we have 2 different sizes of angles and we have 2 different functions here. The easiest thing to convert out of everything that's there is the double angle. So that cos 2 theta, that first piece, we've got a couple of different things we could go with the double angle of cos 2 theta, but we want to pick the one that's going to at least match what we've got here. And since I'm going to replace this one with something else, and you've got a list of all kinds of identities and formulas that are equivalent, you want to pick something that at least matches the sine theta. And this has x's in it, but we're going to change them to thetas. It's the same. This will work nicely here. So when I sub this in, I put the red part in here. Instead of cos 2 theta, instead of cos 2x, I subbed in this 1 minus 2 sine squared theta. So there's your square that I was talking about before when I said that we're going to be doing quadratic trig today. The trig is still trig. We're just going to have a power of 2 in it. So let's just move that stuff around a little bit, rearrange it so that the highest power is first. We don't generally like to have our leading coefficient as a negative, so we're going to multiply everything by a -1, and that gives us, that means this line right here. I took every one of these pieces here and I multiplied each one by a -1 to get rid of the negatives. I did the same to the right side, and that of course stays as 0. So they've all changed to positives. You can also think of this as, instead of, if you don't like that multiplying by -1, you can think of it as bringing everything over to the other side. That becomes a -1, that's a negative sine theta, and that's now a positive 2 sine theta. So you could think of it that way too. Okay, so now we have this quadratic, what you're looking at here. But it might look a little crazy. So here's a little strategy. If we let a equal sine theta, then I can replace this stuff here. I can replace this easily with an a, and this, because it's squared, would be an a squared. That's, whoops, and then an a squared there. So I write it out like this, and now we're back in grade 10. We're feeling really comfortable with this. You know how to factor that. We're up here at the trinomial factoring. So I want you to press pause and remind yourself of how to factor it. If you're doing sum and product or decomposition or whatever it is, I'm not going to review how to factor a trinomial here. I'm just going to jump to the answer. So give yourself a minute to factor it and then come back. So here's the answer. That is factored. It doesn't, you could have had the brackets in the other order. You could have had your a minus 1 first and then your 2a plus 1. That's the same thing. So we have two factors, which means either 2a plus 1 is 0 or a minus 1 is 0. If either of those are equal to 0, then our whole thing will equal 0. Simplifying each of these little mini equations here, simplifying for a, we get a equals negative 1/2 or a equals 1. So that seems pretty, that's all grade 10. This whole section right here is all grade 10. So now remember that we actually put the a in ourselves. We have to go back and put a sine theta in for that. Sine theta equals negative 1/2 or sine theta equals 1. And now we have to solve this part. So the first one, remember that sine, I'll put it up here on the left, sine is equal to opposite over hypotenuse, or it's equal to y over r. So I'm looking first at that sine theta equals negative 1/2. If I have a negative 1/2 here, I know that the r has to be positive, so the y must be the negative. So my y is a negative 1 and my radius is a 2. I'm going to draw that on a diagram. Y value of negative 1 means I'm looking at the lower two quadrants. That's where a y value of negative 1 will be. So y value of negative 1 and r value of 2 could be here. Draw a triangle here. There's this rotation in here. My opposite, or my y value, is a negative 1. My hypotenuse is a 2. What is that angle that I drew in blue? What is that large angle? You might need to start first with the smaller angle. Remember, we're in degrees. This is the 30-degree angle, which means the entire rotation is going to be 180 plus 30. So we get our first answer of 210 degrees. So we have this theta here. Theta is 210 degrees. I'll put a theta 1 there. That's our first answer. We've got more. Let me switch colors so we don't get confused. So back to my little Cartesian plane. I can also draw that triangle here. Down here, oh, there's my right angle. So there's my negative 1 for y value, 2 for r, and then this is a root 3 up here. That doesn't really matter. So what's the red rotation to the terminal arm there? How many degrees is that? If the related acute is a 30, if that's 30 degrees in there, then the whole rotation is going to be 360 minus 30, theta 2, will be 330 degrees. But we're not done. That just takes care of this piece. I still have another section over here. I have sine theta equals 1. When we have a 1, draw another quick x and y axis. When we have a 1, we're always thinking of the unit circle. So a unit circle on here should have a radius of 1, meaning every coordinate, like that first point there, its coordinate is 1, 0. Up here we have 0, 1. Down at 180 degrees, that coordinate is negative 1, 0. And down at 270 degrees, we're at 0, negative 1. So I'm looking for where sine theta is 1. Sine theta equals 1. That's 1 over 1. Again, it's y over r. So they both need to be a 1. So where on this circle can I have a y value of 1, and the radius is always 1 on the whole unit circle. This is a given, right? I don't need to worry about that. But where is the y value equal to 1? There's only one place, and it's rotating right up to here, to 90 degrees. There's my y value of 1. So I have another answer. My third answer for theta, theta 3, is going to be 90 degrees. So those are our three answers. Let's just put them in order. Therefore, theta can be 90. Don't forget the degree symbol. 210 or 330. Any of those answers, if any of those degree measurements, if I went back to my original question right here and I subbed in a 90 in here, I would get it to all equals 0. And you can try it with your calculator if you want to, or sub in a 210 or sub in a 330. But once you sub it into the original question, you're going to get 0. You can always check equations with your calculator. When you don't have a calculator on an evaluation, then you can just check by subbing in on your own. Just do, if I subbed in a 90, a cos of 2 times 90, that's cos of 180. I know that cos of 180 is -1. Sub in a 90 here. Sine of 90 is 0. I'm sorry, sine of 90 is 1. We get -1 plus 1 is 0. So you can check. If you have time, you can check. And it's good practice anyway to make sure you understand all of the steps of solving an equation. So that was a quadratic linear equation because we had a power of 2 in there. We had to factor it. That's what made it, that's back to the grade 10 quadratic. Oh, let me erase so you can see what I put over here. I just put this part in because sometimes students get confused with power of 2 when as soon as we get to this trigonometry. So sine theta plus sine theta is 2 sine theta. It's not sine squared theta, and that's unfortunately a mistake that students make too often. Sine theta plus sine theta, again, change it to an A. A plus A is 2A. It's not A squared. To get a squared, you have to multiply sine times sine. Example 2. Solve this equation for the domain. Remember, the square brackets mean from 0 to, this is your leftmost endpoint, this is your rightmost endpoint, from 0 to 2 theta. This is interval notation. Find exact solutions where possible, approximate solutions otherwise. So we'll get to that. Okay, what are we going to do here? This is our equation. We've got a sine and a cos. It's okay that this one is squared and this one is not. It's only a problem if one's a double angle and one's a single angle. But our angles are both single angles here. This whole function is squared. Again, that's like an a squared, no problem. But this isn't an a. So when I take my equation, the first thing I want to do is write everything in terms of sine or cosine. So what's easier to swap out? Is it easier to take, so you have your formula, all your formulas somewhere handy, right? You have all your formulas. Do you have something that's easy to swap out for a sine to turn it into a cos? Or would you rather take a cos, now that's not squared, and put it into a sine? So my recommendation is going to be the Pythagorean identity. It's very helpful when you have squareds. I have sine squared plus cos squared equals 1. So I'm just going to rearrange this identity right here. I want to isolate cos squared, so I'm going to bring sine squared over here. And then, sorry, I'm going to do it the other way around. I'm going to isolate for sine squared because I want to put in for sine squared here, I want to use the cos squared. Sine squared is equal to 1 minus cos squared. So now I have matching trig functions. I have coses. That's perfect. So let's drop off those brackets by multiplying the 6 in and rearrange it. And I don't like that negative leading coefficient, so I'm going to multiply everything by -1. And we have this. And now we have our quadratic. Again, you can let cos x equal a if you want to work with a more recognizable trinomial. You can do that, or if you're okay with it, leave it as a cos right now. So I'm not going to show you the step where I put the a in and I make it 6a squared plus a minus 2, but you can do that. So now comes the factoring. This is the grade 10 part. So my next line is going to be the factored line. So it's good for you to pause right here, work on your factoring, and then come back and see if it factors the same. Okay, so if you factored it and you used a, you need to switch it back out for cos now because I didn't switch to a. So there's my factored line. 3 cos x plus 2, 2 cos x minus 1 equals 0. That means either this bracket needs to be equal 0 because 0 times, I don't care what's here, a million, 0 times a million is going to give me 0. Or this bracket is 0. So that I have to find out answers for both sides, for both brackets. So let's isolate first. On the left, bring the 2 over, divide by 3. We have cos x equals -2/3. And then when we isolate on the right, we get cos x equals 1/2. Now what? So I'm going to start with this side over here first. Cos x equals 1/2. Remember the cos is x over r, or adjacent over hypotenuse. So everything is positive here. I'm going to draw an x and y axis, and I'm going to put an angle here because I know in quadrant 1 cos is positive, so I know I'm okay there. I also know that in quadrant 4 cos is positive, so I'm going to put another one down here in quadrant 4 in a minute. So my first angle x is here. You can make it a theta if you want to. This triangle right here has a value of 1 here, a value of 2 for the hypotenuse. So what is this one's in radians. If you look at the question, our domain is in radians. What is the angle equal to in radians? This is a √3. This one is going to be pi over 3. This is pi over 3. So my first answer I'm getting is x equals pi over 3. Now there's another answer because there's always two. When you have an unknown angle that you're solving for, there's always two places it could be. X is positive in quadrant 1 and in quadrant 4. So let's draw our angle down here in quadrant 4. There's quadrant 4. That acute angle in the corner there, the vertex, is pi over 3. So what is the rotation all the way to that terminal arm in quadrant 4? That's going to be 5 pi over 3. So there's our answers for the first part, and we didn't switch out, we didn't have a double angle or anything that we changed our period. That didn't happen. We always had a single angle all along. Right up here in the original line here, we've got a single x and a single x. There was no double angles, so I don't have to worry about, do I have to add on a period? Is there another rotation? There's not. Now we're going to look at the more challenging side, which is the left side here. I've got, this is again adjacent over hypotenuse, or x over r, but I don't have a triangle for that. The negative tells me, the negative there tells me that I'm going to be in quadrants 2 and 3, but I don't have a triangle. Let me just draw one here. So here's a triangle. Here's my angle in here, where my adjacent is a 2 and my hypotenuse is a 3. We don't have a triangle that we have memorized for that. So in this case, if you have this on a test or a quiz, you would stop here. You can't go any further without a calculator. And if you look up to the original question, it says find exact solutions where possible. We did that. Approximate solutions otherwise. So we're going to go ahead and finish it with our calculators, because certainly on future evaluations, like an exam, you're going to have your calculator. So we need to finish this question here. We know we're in quadrants 2 and 3. So the first thing you're going to do, please, is get out your calculator and write down what your calculator gives you there. So press pause for a second while you figure this out on your calculator. Make sure your calculator is in radians. You done? Okay, hopefully your calculator gave you something like x equals, I'm going to put a dot there, approximately 2.3. We're not going to put too many decimal places down. So about 2.3. That's the one answer, and your calculator is only going to give you one answer because you're smarter than your calculator and you know there's another answer. Cos is negative in 2 quadrants. We already talked about that. Quadrants 2 and 3. Here's 2, here's 3. Cos is negative in both of those quadrants. So I've got my 2.3. Now that's radians, 2.3 radians. So if we're writing in terms of radians, remember this is 0. Over here is pi, but since I'm using decimals right now, I'm going to put that as a 3.14. I've got a 2.3. 2.3 is, let's say here, that's 2.3 radians right there, 2.3. That's my first answer. Now, how are you going to find your second answer? The second answer that I'm looking for is going to be down here, right? It's got to be in the same quadrant, but whatever this beta angle is, this beta angle has to be the same thing. So on your calculator, you're going to have to do, there's a couple of ways to do it, but to find beta, you're going to have to take pi and subtract 2.3. That will give you your beta angle. Then to find your new rotation in quadrant 3, you're going to have to take pi and add on the beta angle. So once you do that, you should get another answer of x is approximately, I've got 3.98 here. Oh, I used 2 decimals and 1, so this was a 2.30. There are your 4 answers. We're going to put them in order. Now, these last ones that I wrote in black, you wouldn't be able to get without your calculator anyway. So we'll just do what we've got here. We'll do all 4 of them. So all 4 of these, which one is the smallest number? Pi over 3, 5 pi over 3, 2.3, or about 4? Which one's smallest? Pi over 3 is smallest. So x is equal to pi over 3. And that's in quadrant 1. That's the smallest one over here, right? This is quadrant 1. Of course, it's the smallest one. The next biggest one is way over here in quadrant 2. That's my 2.3. 2.30 technically. The next one was in quadrant 3. That's the 3.98. And then 5 pi over 3 is my last one. And those are all in order, and those are all of my answers for x. On a tester quiz, if you don't have a calculator, you wouldn't be able to go anywhere past what I wrote in red there. I'm going to erase all of this on the side here because I'm going to show you something here. So just if you haven't copied it down, press pause and copy it down because I'm about to erase it. So I just want to show you what this would look like graphically. If you're typing this into Desmos and you're solving it graphically, the left side would all be one line in Desmos, and then 4. This is technically, you would be typing y equals 4. This is y equals this, y equals this. You type that all into Desmos. I'm looking for where this weird wave shape, whatever this is going to equal 4. It's going to have a y value of 4. So there's the diagram. There's my y value of 4. That's this horizontal line. And here's what this wave looks like. You don't need to know that it would look like that, but that is what it is. And then when you click on the points of intersection, up come the values. So Desmos is giving us some exact ones there, pi over 3, 5 pi over 3, just like we were able to do, but then the other ones were decimal values here. So that is how you can check your work on Desmos. All right, example 3. I like doing these questions because you get to bring in all your knowledge from so many things together to solve a problem. So let's look at A first. First of all, we're in radians, not in degrees. So I put the little radian angles here for you. Notice that we have different angles. Here's a double angle and here's a single angle. So we're going to have to deal with that. We're going to need to go with a single angle, but both are cos, so that's good, but I still have the problem of double angle. However, you look at your cos 2x, you look at your double angles, and you'll see lots of things we can trade out with, and we want to switch it with something that's going to match with this cos single x angle here. So hopefully you have found the same thing that I found, and we're going to use 2 cos squared x minus 1. So the 10 is a 10, but instead of cos 2x, instead of this piece, I'm switching that out for 2 cos squared x minus 1. And then minus 8 cos x is fine. Plus 1 equals 0. So we're just going to distribute that 10 in, and we have 20 cos squared x minus 10 minus 8 cos x plus 1 equals 0. We have some constants to collect, and we're going to put this in order. So my highest degree goes first. That's my 20 cos squared x. That's going first. Then minus 8 cos x. And finally, minus 9 equals 0. And my leading coefficient is positive. Great. Now you are maybe saying, well, I want to let A equal cos x, and I want to change all of this to a's, so that would be 20a squared minus 8a minus 9. I'm going to erase that though, because I'm not going to do that, but you can. So right now you're going to factor and then press pause, and when you come back you will see the answer to the factoring, but with cos's in it. There won't be any a's in it. And there's my factored line. So my first bracket right here, that's telling me I'm looking for where 10 cos x minus 9 equals 0, which is the same as where cos x is equal to 9/10. I don't have a triangle for that. I'm going to have to use my calculator. And this one tells me I'm looking for where 2 cos x plus 1 equals 0. Isolating for cos x, we have cos x equals -1/2. Now I think I have a triangle for that. So let's start first with the 9/10, which I don't have a triangle for. You'll get your calculator out and you're getting x equals approximately 0.45. That's one answer. Now we have to find all of the possibilities. The original question was cos x equals, not the original, but the line above this one was cos x equals 9/10. That's a positive. Where is cos positive? Here and here. So the answer, the first answer we have, 0.45, that's this little tiny angle right here. That's 0.45 radians. So I'm going to take that, put it down there in quadrant 4. There's my 0.45. And I want to rotate all around there. What I'm going to be doing mathematically is 2 pi minus 0.45. That will give me my second x answer. So my x1 is 0.45. My x2 is about, so it's 2 pi minus 0.45, 5.83. Okay, there's my two answers. I've got both quadrants, so I'm sticking within my domain for the question. Now let's look at the cos x equals -1/2. Do I have an adjacent over a hypotenuse? Do I have a triangle that would have, here's my angle in here, where the adjacent is a -1 or 1, and the hypotenuse is a 2. Put that on a Cartesian plane. So I drew it that way because I knew that cos is negative in quadrant 2, so that's why I oriented it that way. Look up at the triangles above here. Which one is that? We're looking for an adjacent of 1 and a hypotenuse of 2. That's going to be pi over 3. So this related acute angle is pi over 3. Pi over 3 is not my answer. X does not equal pi over 3 because that pi over 3 is over here. That's where pi over 3 is. Right over here, that black arrow in the second quadrant, that's going to be 2 pi over 3. So I've got x, oops, wrong color, x equals 2 pi over 3. That's my x3. And I have another one, a fourth answer, because cos is negative in 2 quadrants. So I take my pi over 3, I draw it down here, pi over 3, put it down here in quadrant 3, rotate to that terminal arm. That rotation is going to be a full pi rotation plus another pi over 3. So that's going to be 4 pi over 3. 4 answers, and let's just tidy them up and put them in order. There we go. There's our 4 answers. 2 of them are exact and 2 of them are approximate. Let's do part 4. So I recommend here, just try it yourself. Just get started. We only have 1 cos in here. You're not going to have a whole lot of calculations to do. We don't have to substitute anything else, so give it a try on your own. But, of course, I'm going to do it with you here. So let's get that, divide both sides by 4 to get rid of that 4. And we have cos squared x equals 3 over 4. Okay, but I need cos x in order to do all this kind of work that we see here. We need a single angle and not a squared function. So how am I going to do that? How am I going to get rid of a power of 2? Well, you know this already. To get rid of a power of 2, we square root. I'm going to square root this side, and I'm going to square root this side. And the power of 2 cancels out with the radical. So I now just have cos x equals, so this is plus or minus, because we can have a positive or a negative, plus or minus root 3 over, now the square root of 4 works out nicely to a 2. I don't need to put another plus or minus here because the above plus or minus has all those combinations in it. So that, let me just write that out again. What I've got here is cos x equals root 3 over 2 and negative root 3 over 2. I've got two answers. Do I have triangles for that? That looks like I just might have a triangle for that. Let me draw it out here. A triangle. I've got an adjacent of a root 3, a hypotenuse of a 2. That makes this side a 1. So the angle in here that we're looking for is the pi over 6. So we're looking for a pi over 6. And this is a unique case because we've got plus or minus. So where is cos positive? And we want to know where is cos negative? Everywhere. That's every quadrant. Every single quadrant we're going to use for this answer. So I'm going to take the pi over 6 and I put it in quadrant 1, I get pi over 6. When I put it in quadrant 2, I'm going to get 5 pi over 6. When I put it in quadrant 3, I'm going to get 7 pi over 6, and then quadrant 4 is 11 pi over 6. So I've got root 3 over 2 in every quadrant. Therefore, x equals, start with the smallest one, that was the pi over 6, that was quadrant 1. In quadrant 2, that was 5 pi over 6. In quadrant 3, 7 pi over 6. And in quadrant 4, 11 pi over 6. Again, there's no double angles here, so I didn't have to worry about going back and looking at the period. In our first question, we did have a double angle up here. We had a double angle, but we actually replaced it so that we wouldn't have to deal with a double angle, so we didn't have to worry about changing the period there at all. Last example, solve the equation sine x minus root 3 cos x equals 0. We're in radians, and we're going to check our answer. Okay, we've got a sine and a cos, not good. We've talked about this before. When you look at your list of all of your equivalent equations, equivalent expressions for sine and cos and tan, there's not a lot with just a single sine x, or that's not squared or not a double angle. So we have this strategy we did in our last lesson, if you remember what it was. Do you remember what it is? Let me start off by just bringing this piece over to this side, and we'll have sine x equals root 3 times cos x. So you remember what we did there? We divided both sides by cos x, which I said before, you normally can't divide by a function, but in this case it's unique because sine x over cos x is the same as tan x. So when we're talking about restrictions, which we don't need to do restrictions, they would be the same for tan x as it would be for sine over cos x. So we're not, it's okay to divide by cosine because tan is sine over cos. So cosine isn't truly eliminated. It is still part of the tangent function, and that's what we have to be careful around. We couldn't divide both sides by sine, because if we divided both sides by sine, that would actually eliminate some solutions. Well, that's not possible here, but we can divide by cos. These are gone. Tan x equals root 3. Lovely. You know what to do with that. That's really root 3 over an invisible 1. And tan is y over x, or opposite over adjacent. Look at your triangle. Do we have a triangle where we have, so here's my theta, which is an x. My opposite, do we have an opposite of a root 3 and an adjacent of a 1? Yes, we do. The hypotenuse in this case would be a 2. That is pi over 3. We have, our question here says 10 is positive. There's a plus sign that you can't see it, but there is a plus sign there in front of it. So we can actually use that answer of pi over 3. That's going to be one of our answers. We get x equals pi over 3. Now, where else can we put that? So let's throw x and y axis here. Where else can that go? Where else is 10 positive? What other quadrant is 10 positive in? 10 is positive where? Castrol. 10 is positive down here in quadrant 3. So you take your pi over 3 angle, you throw it down there in quadrant 3, and you rotate around to it, and you get 4 pi over 3. X is equal to pi over 3 and 4 pi over 3. That looks great. We also had an extra instruction here. Check your answer. We want to check our answers. How do we do that? So this is the great thing about solving equations. If you have time, the question didn't tell you to check your answer, you wouldn't have to, but this one does, so we have to, and it's always good to do. So let's do a check. Let's first check our first answer. We got x equals pi over 3. Let's check that one first. So you can do your check with a left side, right side, or you can do a t-chart, but you have to do them separately. You can't bring things across the equal sign. So I go up to the original equation. This is my original equation here. Let me write that out. Sine x minus root 3 times cos x equals 0. So if you're doing the t-chart method, you're going to draw a line straight through the equal sign, like this, and like this. And now I'm going to sub in x equals 3 into these values here. I don't have one to sub in on this side, so the right side is going to stay as 0. That's an easy side. I don't have anything to do there. Always substituting into the original equation, always. We've got sine of pi over 3 minus root 3 times cos of pi over 3. So I'm only working on this side right now. What is sine of pi over 3? I already have a pi over 3 triangle drawn up there in red. Sine is opposite over hypotenuse, so that's going to be root 3 over 2. Minus, now here's that root 3. What's cos of pi over 3? Cos of pi over 3 is adjacent over hypotenuse, so it's 1 over 2. I get root 3 over 2 minus, multiply across, straight across the top. Root 3 times 1 is root 3. 1 times 2 is 2, and of course we get 0. So since the left side equals the right side, that means our answer pi over 3 is correct. It does not mean the answer is 0. It does not mean x equals 0. That's not the right answer. So since the left side equals the right side, since they balance, then what we have proven is that x equals pi over 3 is correct. So we've proven that one. But we have to check both answers. So I'll just show you, instead of the t-chart, another way to check. We're going to check x equals 4 pi over 3. To do that, I'm just going to do the left side, right side format. Left side is sine x minus root 3 times cos x, and the right side is 0. Subbing into the left side, 4 pi over 3 minus root 3 times cos of 4 pi over 3. Okay, what is sine of 4 pi over 3? So first I'm going to figure out sine of pi over 3, and then I'm going to put it in the right quadrant. I'll just draw the triangle again right here because it's getting a bit messy. Here's pi over 3, root 3, 2, and 1. So sine of pi over 3 is equal to root 3 over 2, but I want 4 pi over 3. 4 pi over 3 is in this quadrant down here, quadrant 3. 4 pi over 3, and sine in that quadrant is negative, so this must be a negative root 3 over 2. Subtract root 3 times cos of 4 pi over 3. So cos of pi over 3, cos of pi over 3 up here in the top right, I'm putting it cos of pi over 3. There's pi over 3. Cos is adjacent over hypotenuse. It's 1 over 2. But 4 pi over 3 is in quadrant 3. Cos is negative there. So I'm going to multiply that by negative 1/2. That gives me negative root 3 over 2 plus root 3 over 2, which is 0, which is the same as the right side. Therefore, left side equals right side, so x equals 4 pi over 3 is correct. If the question asks you to check your answer, you must check your answer, and you can do it with either of these two ways that I've shown here. You can either do a t-chart or you can write it out left side, right side. It's really no difference. But you can't move things across the equal sign, and you have to go to the original question. So this is how you check your answer. If the question tells you to, you have to. It will be worth marks. It will be worth marks to show that you can do this. So you can't just skip it. And why not do it anyway? Because once you do it, then you know your answer's right, and then you feel good about that. That's the end of solving quadratic trig equations, and that's really the end of this chapter we've been doing on trigonometry. So at the end here, we're pulling all of our skills together that we've learned about trigonometry to solve these questions here. So if you're able to solve these difficult, or even more difficult than this, able to solve these questions, then you've really got a good handle on your trigonometry.